So let's continue exploring the simple harmonic oscillator, where the potential looks like 1/2 times some constant times x squared. So if we plot that, then it looks like that. So let's get a sense of what the energy eigenfunctions look like. So, right, so we have some lowest value. Then we have an excited state and an additional excited state and so on. Let's draw these functions. So they have to respect the symmetries. So it's not obvious at this point that the energy quantum number for the lowest state, for the ground state, will be n equals 0. Nonetheless, let's use that value. So the ground state, what does that look like? Well, right here are the turning points. So the particle is not allowed classically to be out beyond this point here and to the left of this point. And we know that the bending of the function changes from here to there. So the ground state has no nodes, and it has to be an even function. So if these points represent the turning points, then the function looks something like that. Now so first of all, this is not a sine or a cosine, because in here the difference between E naught and the potential is changing, so it's not a constant. So this is so we have to notice that. It's a little bit tricky to draw that. The same is true out here, right? The difference between this and this is increasing as we're going further and further away. But nonetheless, the bending has to be the other way. So it has to die off like that. It has to be an even function. For psi1, the first thing to notice is that we are moving further away. The turning points are further away. And so if we do something like this, so we're further away than we are here, then we have the odd function, right? We have the symmetry of the potential, and so the solutions are alternately even and odd. And so we're still bending toward the axis here. And we have to come through 0. Kind of missed the 0 there. And then I have to be an odd function. And I bent too much here. Not the greatest drawing, but right, so it should be the same as this. If I flip this and flip it again, I'll get that function there. Dies off, something like that. That's psi1, and now we can do psi2. And I'm going to be even further away, right? So the turning points are even further away, so, but let's not overdo it, otherwise I'm not going to have any space here. So what does that look like? Now I have an even function. It dies off. It does something like that. It goes up like this. It has to come down and come back up, and then bend away like that. It's also important to point out that the amplitude here is smaller and the amplitude here. And that has to do with difference between the energy and the potential. The energy, so we're here, the energy difference between this and this is larger here, closer to the midpoint, x equals 0. So there's greater bending, whereas as we're approaching the turning points, that difference gets smaller. And so, again, we can say the bending has to be less, or we can think of it in terms of momentum being smaller, and so the particle sort of hangs out in these regions more. This is a generic feature of all these eigenfunctions. And maybe the last thing that we can point out is that this is kind of like the infinite square well, where the energies go like n squared over the width of the well, L squared, but such that as the energy increases, the well length increases, and so we should find that the energies will be discrete, but they also won't increase as rapidly as the quantum number squared, because this quantity is also increasing, and we'll see that.